Good day, everyone. This is Francis Deo Pansoy, and I will be reporting about water quality models. So let's start. Water quality models can be useful tools to simulate and predict the levels, distributions, and risks of chemical pollutants in a given water body. So this compromises every chemical pollutants depending on the water body itself. So the modeling results from these models under different pollution scenarios, because every body of water are having or experiencing different pollution scenarios. Very important components of environmental impact assessment, and can provide a basis and technique support for environmental management agencies to make right decisions. So when dealing with the water quality models, we are looking or we are considering of these indicators or parameters. First is the physical indicators. So the temperature, the turbidity of the water, electric conductivity, and viscosity, and etc. Next is the chemical indicators, the pH value, if it is acidic or basic, metal, salt, nitrate, phosphate concentration, dissolved oxygen, pesticide concentration, and many more. Next is the biological indicators. So this includes bacteria, parasites, viruses, protozoa that are present in the body of water. And lastly, radiological indicators. So radioactive elements such as uranium and etc. So next is the development of surface water quality models. So before we develop the water quality models, the following are customary to define: the physical, chemical, and biological element of water quality itself. So the deterioration of the quality of surface water, groundwater, and coastal water systems is mainly controlled by the geological structure and the lithology of the watershed's aquifers, the chemical reactions that take place within the watershed or aquifer, as well as the type of land uses and the anthropogenic activities. So that deteriorates the quality of surface water or any types of bodies of water. So for water quality modeling, this involves water quality based data using mathematical simulation techniques. And it helps people understand the eminence of water quality issues, and models provide evidence for policymakers to make decisions in order to properly mitigate water. So for example, there is a barangay or a barrio somewhere that is having water quality issues. So the government can make decisions based on the results from these water quality models. So it also helps determine correlations to constituent sources and water quality, along with identifying information gaps. It also consists of a collection of formulations representing physical mechanisms that determine position, momentum of pollutants in a water body, and also available for individual components of the hydrological system, such as surface runoff. We all know that already. There also exist basin-wide models addressing hydrologic transport and for ocean and estuarine applications. So almost all scope of water bodies are being considered in water quality models. So classifications of water quality models. So this depends on what type of the classification of the water quality models. So firstly is the type of approach. So this is physically based, conceptual, or empirical. Next is the pollutant item. So if in the body it has nutrients, sediments, salts, etc. Next is the area of application. So for catchment, groundwater, river system, coastal waters, and integrated bodies of water. Next is nature of the water body. So if it is dynamic or stochastic, state analyzed, if it is in steady state or dynamic simulation, spatial analysis, if it is lumped or distributed, dimension, if 1D or 2D models are needed, and data requirements, extensive databases, or minimum requirements models, or MIR. So those are the classifications of water quality models. So next is building a model. So water quality models have different information but generally have the same purpose, which is to provide evidentiary support of water issues. So all builds up to providing support for the water issues. Models can be either deterministic or statistical, depending on the scale with the base model, which is dependent on if the area is on a local, regional, or a global scale. So another aspect to consider for a model is what needs to be understood or predicted about the research area, along with setting up any parameters to define the research. So if that area is a very rich area, meaning there are lots of nutrients, so you need to consider that or to understand those parameters needed. Another aspect of building a water quality model is knowing the audience and the exact purpose for presenting data, like to enhance water quality management for water quality law makers for the best possible outcomes. So again, in the end, we are expecting to have water quality that is safe for every uh, consumers or everyone. Next is water quality is modeled by one or more of the following formulations. So a water quality is based or it is made by one or more of these formulations: the advection transport, the dispersive transport, the surface heat budget, dissolved oxygen saturation, reaeration formulation, carbonaceous deoxygenation formulation, nitrogenous biochemical oxygen, sediment oxygen demand, photosynthesis respiration, pH and alkalinity, nutrients formulation, algae formulation, zooplankton formulation, and coliform bacteria formulation. So the water quality model is based on what is present in that body. So there. Next is the first quality model that was developed is called the S-P model. It is published by the sanitary engineer Harold Warner Streeter and the consultant Earl Bernard Phelps way back in 1876 to 1953. Based on the data obtained from May 1914 to April 1915 by the United States Public Health Service under supervision of Surgeon W. H. Frost. So the data have been gathered from May 1914 to April 1915. And as the years go by, more complex versions of the model were introduced during the 1960s, where computers made it possible to include further contributions to the oxygen development in streams. So this is the first model, the SP model or the Streeter-Phelps model, and this is their equation. So the Streeter-Phelps equation determines the relation between the dissolved oxygen concentration and the biological oxygen demand over time and is a solution to the linear first-order differential equation. So the equation goes like this. Uh, dd over dt is equal to k sub 1 L sub t dash k sub 2 times d. So this differential equation states that the total change in oxygen deficit, or the D, is equal to the difference between the two rates of the oxygenation and the aeration at any time. So assuming a plug flow stream at steady state, the Streeter-Phelps equation is this. D is equal to K1 L sub A over K sub 2 minus K sub 1 multiplied by E to the power of negative K sub 1 T minus E to the power of negative K sub 2 times T, then plus D sub A times E to the negative K sub 2 T, wherein D is the saturation deficit and K1 is the deoxygenation rate, K2 is the reaeration rate, LA is the initial oxygen demand, LT is the oxygen demand remaining at time t, dA is the initial oxygen deficit, T is the elapsed time, usually D. Applications and limitations of this water quality model. So the applications is that assuming that a single BOD or biochemical oxygen demand input, so only one, is distributed evenly at the cross-section of a stream or river, and that it moves as a plug flow with no mixing in the river. Furthermore, only one DO sink carbonaceous BOD and one DO source reaeration is considered in the classical Streeter-Phelps model. So it is considered as a very simple model because there is only a single biochemical oxygen demand or BOD input and also one DO DO or dissolved oxygen source reaeration is considered. So uh, these simplifications gave rise to errors in the model. So as time goes by, they developed it. They considered all the parameters, especially the DO or the dissolved oxygen demand. So expanded SP model, as I've said, it is developed. So this is a modification of the traditional model and includes internal sources such as reaeration and photosynthesis and sinks, BOD, biochemical oxygen demand, background BOD, SOD, and respiration of the DO or the dissolved oxygen. Parameters in the expanded model can be either measured in the field or estimated theoretically. So that is how they solved it. For background BOD, so this is the formula. dL over dt is equal to negative K1 L plus LB. So for background BOD or benthic oxygen demand, this is the diffuse source of BOD represented by the decay of organic matter that has already settled on the bottom. This will give rise to a constant diffuse input, thus change in BOD over time will be that said formula, wherein K1 is the rate of oxygen consumption by BOD, L is the BOD from organic matter in the water, and LB is the background BOD input. So next one is the sedimentation of BOD. This does not directly consume oxygen, and this should therefore be taken into account. So this is done by introducing a rate of BOD removal combined with a rate of oxygen consumption by BOD, giving a total rate of oxygen removal by BOD. So the formula is this: Kr equals K1 plus K3. K1 is the rate of oxygen consumption by BOD, and K3 is the settling of the BOD. The change in BOD over time is described as dL over dt is equal to negative Kr times L, where L is the BOD from organic matter in the water, and Kr is typically in range of 0.5 to 5 d to the negative 1. So the next one is SOD, or the sediment oxygen demand. So they are different. So oxygen can be consumed by organisms in the sediment. So if there are sediments, usually they have small organisms in there which also consume oxygen. So this process is referred to as the sediment oxygen demand. Measurement of SOD can be undertaken by measuring the change of oxygen in a box on the sediment or benthic respirometer. So the change in oxygen deficit due to consumption by sediment is described as dD over dt is equal to negative K2D plus S over H, where H is the depth of the river, S is the SOD, the demand itself, D is the saturation deficit, and K2 is the aeration rate. So next one is the nitrification. So ammonium is oxidized to nitrate under aerobic conditions. So ammonium oxidation can be treated as part of BOD. So this means that the ammonia or the ammonium is consuming oxygen also. So this affects the oxygen demand of the water body. Therefore, the formula is formulated uh, by this: d over dt is equal to k sub n times n minus k sub 2 times d, where d is the saturation deficit, kn is the nitrification rate, n is ammonium nitrogen concentration. Next one is the photosynthesis and respiration. So on that two processes, they also require oxygen, right? So the oxygen demand is being depleted somehow. So also they are performed by algae and macrophytes. Respiration is also performed by bacteria and animals. So assuming steady state, the change in deficit will be, so dd over dt again is equal to negative K2 times d plus R plus P average, where R is the respiration and P is the photosynthesis. There goes the last one for the uh, expanded SMP model. So there are also other quality models that have been developed over time. So these are some of them. The drain mod. The drain mod model allows calculating at the scale of an individual field. So the daily nitrate leaching for a given crop, farming soil, and geohydrological conditions. Next is the export coefficient model, or the ECM. So this one, uh, the approach of ECM aims to predict the nutrient loading at any surface water sampling site as a function of the export of nutrients from each contamination source and the catchment above that site. So this deals mostly with the nutrients, especially from each contamination source in the catchment above that site. Next one is the Mike 11. The Mike 11 is a one-dimensional hydrodynamic model that simulates the dynamic water movements in a river. It requires large amounts of data and remains a deterministic model. So that's about Mike 11. Next is the Moneris. So the Moneris, uh, it's abbreviation for modeling nutrient emissions in river systems. For short, Moneris model builds over 8 submodels that stimulates the main processes of generation and transport of suspended solids and nutrients to the river network. So this is a more complex model compared to the export and drain mod there. So these water quality models are very important to predict the changes in surface water quality for environmental management in the world. So worldwide, hundreds of surface water quality models have been developed. Moreover, some developed countries provided some regulated models for surface quality simulation. Therefore, it is very necessary for most developing countries to standardize some widely used water quality models for efficient environmental impact assessment. However, it is also a big challenge to standardize these models based on their own country's actual conditions, as a lot of investigations and researches are needed. So, especially us in here in the Philippines, we are still a developing country. We have to invest in these water quality models because it is also for us to be safe and for our water to be in a high quality, which is not lethal, and it's also because water's worth it. It's our passion, our respect, our effort, our health, and our future are at stake. That's all. Thank you.